Hi friends, this is a problem from finite element method. So on a thin plate. So I have defined this problem in two ways. One is in terms of kg and newtons and millimeters and something like that. And the units here is imperial units, that is a pounds per square inch for Young's modulus, and inches is given in terms with in the place of millimeters, and density is libra is given. Libra is imperial method of measuring weight, lb. Okay, so the problem definitions are same, but the unit only varies. Solution is similar whenever they give in terms of this imperial unit, same value you apply and same method you follow, but unit only you have to notice in terms of imperial. Problem solving method are same, one and the same. So this in this problem what we have to find is nodal displacement, stress and reactions at midpoint. At midpoint we have to find all these things. So this is a thin plate, but this sketch looks like a stepped bar, but actually it's a thin plate. Okay, so area at midpoint we have to find first. At the midpoint of the plate, 60 here, this is 30, so at the midpoint 60 plus 30 by 2, that is 45 millimeters square. So area for element 1, 60 plus 45, element 1 is this area, this we have to consider. This is for element 1, so this is 60 centimeter. Here 45 we just calculated, so that is 45, like that we'll get 52.5 millimeter square. And next, area of element 2, that is this area, this portion, that is 45. So from here it is, this is 45 and this is 30, so we'll get 37.5. okay, this is when the midpoint, when we are asked to calculate at the midpoint, so this is the easiest way. But if somewhere else, if they ask to calculate it in one particular other point, so at that time to find out this 45 mean this values, so you have to go through this equation. Okay, if other than midpoint is asked, so follow this equation. A2 here, A2 will be this one 60, this one A2 60, sorry, A2 is 30, A2 is 30, this one A1 is 60. Okay, A1 is 60, so at that time A2 30, A1 is 60. The length is whole length you have to calculate, consider, that is 240 millimeter. 240 into 120, 120 is part. If it is here, maybe it is 100 or 80 or something like that. So now I'm calculating for this one, that is why 120 it is. Okay, if any other value they give, then you have to consider, they will be mentioned here aside like this. Okay, next, area of element 1. So for to calculate area of element 1, if other than midpoint, so follow this equation, and for element 2 follow this equation, you will get two values, a1 and a2. if it is midpoint, you can calculate like this easily. Next is what we have to calculate is stiffness matrix. The equation of stiffness matrix, you know it, a e by l into 1 minus 1 minus 1 1. So substitute the value. A is a1, here element 1 we have 52.5, so 2 Young's modulus is given, 2 into 10 to the power 5 divided by 120, L 1, this one. For element 1 we are calculating, so the length will be 120 millimeters. Next, similarly for element 2 also, element 2 now A2 is 37.5, so 37.5 you have to substitute and you'll get for K1 and K2 you'll get. So next, the force vector due to self weight. Force vector due to self weight is equation A1 into L1 into rho by 2 to 1 to 1. So substitute the value, you'll get f1 two values, and here for element 2 as well you'll get f2 value. So now global stiffness matrix k1 k2 we have found out, so add them and you'll get k value. Okay. So next, global nodal displacement vector. There are three displacement, q1 q2 and q3. q1 q2 and q3. Okay, three displacement. So next, load vectors 0 here, 1 2 here, 2 3. So 1, that is 0.2413. next, this is 0.2413, here 1 is 0.1723. so add them, plus 100 is the load given here. Okay, so load vector 100 it is given, so total you have to put here, and next this 0.1723, this one third one, so 1 2 3. Next, equilibrium condition. This equilibrium condition, substitute, and q1 q2 q3 values we don't have, since this is fixed here, fixed at one end, so that time using this, we cut this. So applying boundary conditions now, 1.5 minus 0.625 minus 0.625 q2 q3 100.4133 0.1723. so this is a polynomial equation, so solve this, you'll get this value. Next, simultaneous equation. This simultaneous equation, substitute, it, right? Cross multiplication, 1.5 into 10 to the power 5 q2 minus here 0.625 into 10 to the power 5 q3, this next this way, and this, so you'll get this. So after solving this simultaneous equation, you'll get q2 and q3 value. So note it down, q is equal to q1 is fixed, and so this is eliminated. Using elimination method, I calculated this one. So after that, stress in each element. This is equation for stress in each element. So next what we find is stress at element 1, that is substitution, and 1.9158 megapascals. So and for element 2, this one. So reaction at support, R is equal to k q minus f. Substitute all the values, it is 0 anyhow. So since the reaction is only at the fixed end, the reactions will be at fixed end. So here is only one fixed end, therefore the reaction at support, so 10 to the power 5 into 0, this into 0 it will be, so minus 0.875, this into this is 0, like this we are multiplying, so this into this is 0, minus symbol here, minus 0.875 into 10 to the power 5 here, let it be minus 0.875 into 1.1495 into 10 to the power minus 3, this into this will be 0, so I did not write whichever is 0, so only available values here, minus 0.241, because we are only considering at the fixed end, so this is 0.241. Therefore reaction, calculate this, you'll get minus 100.8200 reaction at other points other than the fixed end. So R1 R2 R3 value you'll get as this in terms of Newton. Thank you.